Hello all of you. Welcome to the 19th lecture on the course on analysis and modeling in chemical engineering. In this course, we have been looking at the modeling and analysis in the chemical engineering problems. And the example that we have been doing in this week is the modeling of chemical reactors. And in the last class, we discussed some of the example problems on the batch reactor and CSTR. So I want to go further on that and take some more examples before we proceed to the energy balance of chemical reactors. So let us take one example of liquid phase chemical reaction. It is A to some B plus C. It is happening in flow reactor that is having a given rate law for this reaction, that is second order rate law. And let us assume that the molar flow rate of B, that is Y times the molar flow rate of A in the feed, right. Essentially what we are saying in our language that we used in stoichiometry is that the theta B, that is for the flow reactor, the ratio of FB naught by FA naught is equal to Y in this case. What we want to do is to draw the typical Levenspiel plot for this case, and then to identify the best possible choice of one reactor or two reactors in series that requires the lowest overall volume for a given feed rate and a given conversion X. And then for each reactor, we have a choice of either a CSTR or a PFR. And the question asks you that does the answer depend on the value of Y and X, and we have to justify our answer. This is a standard problem on Levenspiel plot. So, we want to do a Levenspiel plot for this case. Just to remind you, the Levenspiel plot is the plot of FA naught by minus RA against X, and from there we can identify whether we have lower volume in a requirement in a CSTR or in a PFR. So, we want to do the Levenspiel plot for this case. So, as it is given, minus A is equal to K CA CB, we use the stoichiometry. So, CA is CA naught into 1 minus X, and CB is CA naught into theta B, which I already have seen. The theta B in this case is equal to my Y plus X. So, basically we have Y plus X there. So, essentially my minus RA in this case is K CA naught squared into 1 minus X into Y plus X. The CA naught is constant, K is a constant. So, in general, what we are trying to do here is, if I look at this particular function FA naught by minus RA, I can again write FA naught as something like CA naught V, and then this becomes K CA naught squared into a function of X and Y, and other parts are constant, right. So, this becomes something like some constant, let me call that constant alpha, divided by Gxy, where Gxy is my 1 minus X into Y plus X. Now, you can clearly see it will form a quadratic equation in X, and now the question is that whether that quadratic function has a maxima or a minima between X from 0 to 1, because the conversion can only range from 0 to 1. Any mathematical function may have a maxima at minima at any point, but if there is a maxima between 0 to 1 of the conversion, then only it is relevant here, or a minima in this range, then only it is relevant here. And accordingly, the Levenspiel plot that is done again in the range of meaningful conversion values between 0 to 1. So, only in that case we have to plot that Levenspiel plot differently if a maxima and minima is coming in that range, right. So, let us look at this particular function and try to see whether it has a maxima or minima or not. So, we have Gxy is equal to 1 minus X into Y plus X, and Y in this case is kind of a constant, that is the value that we are giving in, right. So, we will do a dg by dx or g prime x, and that will be equal to something like this. So, we can expand the first Gxy, this becomes Y minus xy plus x minus x squared, and what we see here is g prime x is simply minus y, sorry, it has to be, yeah, that's correct, right. So, this will give me minus y plus 1 minus 2x, and for a maxima or a minima, this has to be equal to 0, and that gives me 1 minus 2x is equal to y, or x is equal to 1 minus y by 2. And let me call this as some extremum, which can be a maxima or a minima so far. So, now let us find the second derivative of g. Second derivative of g double prime, is going to be the derivative of this, that gives me minus 2, that is less than 0. So, when g double prime is less than 0, we are clearly having a maxima, and a maxima in g of x will correspond to a minima in alpha by g of x y, right. So, therefore, in the Levenspiel plot, we will have a minima, because the denominator having a maxima means the function itself will have a minima there. So, the question now is whether this value, whatever is corresponding to the maxima of g of x, whether that value is lying in the limit 0 to 1 or not, right. So, we have a condition that this value must be in this range. So, the lower limit gives me something like y less than 1, and the upper limit gives me something like y greater than minus 1, right. The second point is not very important here, because y is the ratio of b to a in the feed. So, it cannot be negative anyway. So, this is the main important thing. So, when y is less than 1, in that case we are going to have a minima in Levenspiel plot, and when y is higher than 1, then in that case we do not have a minima, right. So, let me do these two cases. So, my f a naught by minus r a by f a naught by minus r a versus x is going to look like something like this when y is less than 1, and then it is also going to look something like that when y is greater than 1, right. Now, you can argue why it is increasing. Keep in mind that if I find it, you are going to find a minima at x value which is negative, right. So, therefore, we have drawn like this. So, there is a mathematically a minima for a negative x, but anyway that is not giving a meaningful conversion value. So, therefore, I am not plotting it. Okay. Now, in this case, if I want to find which reactor will give me the lowest possible value, there are basically three things that we have to keep in mind. The first thing is, what is the value of y? If y is more than 1, then in that case there is pretty much no option. A PFR will always give me a lower option. No matter what conversion value we look at, the volume of CSTR is something like this, and the volume of PFR is the area under the curve, which is of course less than that. So, when y is greater than 1, then in that case clearly we want to go for a single PFR. On the other hand, when y is less than 1, then there are essentially two cases. The first case is when the conversion value is before this minima. If the conversion is before this minima, then no matter what conversion we have, always the area under the curve is bigger than the area we get for a CSTR. So, in this case, this is what we get for a CSTR, and the area under the curve is clearly higher for the PFR, right. So, for x less than x star, it is clearly again going to be a single CSTR. On the other hand, if we have x higher than x star, in that case again beyond x star a PFR is again advantageous, right. So, what we can then do is, for that case we can employ a CSTR until the minima point, and after that we can follow it up with a PFR, because after the minima the PFR is again advantageous compared to a CSTR, because a CSTR will simply require higher volume than the case of a PFR beyond the minima, right. So, in this case we will go for a CSTR until the conversion of X star and followed by a PFR, right? So we can get these kind of examples, I would say more textbook like examples using Levenspiel plot. So this is very instructive tool to figure out which reactor scheme does work well for the problem, right? Keep in mind that all the examples that I have done so far are isothermal reactors. We are not looking at temperature effects. In all these cases, the temperature is being held constant. We will do cases when the temperature will change in near future. Okay, let us now do the last example. We are doing kind of, in this example, a variable volume batch reactor. We are looking at a spherical rubber balloon which is filled with a reactant gas A at time t equal to 0, and then it starts chemical reaction A going to 3B after time 0, and you can see this reaction basically results in increase in the number of moles, and therefore the balloon is going to expand and balloon will keep on expanding. Let us assume it remains spherical when it has A and B. And then what is it being said is like the balloon may be considered as a spherical cell with some inner diameter d. In the beginning, this is my diameter d, and this is my diameter d naught in the beginning. And there is a cell thickness, small cell made up of rubber. So we have a cell thickness, and the cell thickness is of course going to get smaller with time, and the cell thickness, let me call it some s of t, and we have in the beginning some s naught. And when this cell thickness becomes less than a minimum value Sm, in that case the balloon is going to burst, right? So it is a rubber balloon and it will keep on expanding because of the chemical reaction, and the balloon is going to burst when the cell thickness, that is the rubber thickness, is basically coming down below a threshold, right? We are assuming that we have isothermal and isobaric operation, no changes in temperature and pressure, and the question asks you to find the time required for the balloon to burst in case it burst, and the number of moles of A that is released in the atmosphere after the balloon burst, and it is asking also whether it is possible that the balloon does not burst. And some hint is given that the cell may be considered sufficiently thin so that the volume of rubber at time t is pi d square s. This is only the volume of this cell, not the inside volume, that is some pi d square s naught to begin with, and some pi d naught square s naught to begin with, and then it can be something like pi d square s later. All right. So one thing to note is that it is given in the problem that the density of the rubber is assumed to be constant, and of course the mass of rubber cannot change, and mass is density into volume of the rubber. So that means the volume of rubber, that is only the cell, that is not changing with time. So what this means is my pi d naught square s naught is equal to pi d square s, and that gives me something like s by s naught is equal to d naught by d squared, right? And if I now look at the volume of the balloon, the inner volume of the balloon, the inner volume is going to be something like pi d cube by 6, right? So the v by v naught therefore is d by d naught to the power 1/3, d by d naught to the power cube, and that gives me d by d naught is equal to v by v naught to the power 1/3. If I plug it in there, s by s naught becomes v naught by v to the power 2/3. That is one relation that we can get from the mass balance. Now the question is, what is my v by v naught we get from the chemical reaction, right? So we will assume that the gas inside the balloon is an ideal gas. So in that case, we have PV equal to total number of moles RT at time t, and in the beginning again pressure into volume at time t0 is equal to something like NT0 RT. The temperature and the pressure is not changing. So if I divide this two, this gives me V by V naught is equal to Nt by Nt naught, and the number of moles at time t, this we have done by stoichiometry, that is given by something like Nt naught plus delta Na naught x by Nt naught, where delta is basically the sum over the stoichiometric coefficient. In this case, we have A going to 3b, so delta is essentially 3 minus 1 is equal to 2. So this gives me 1 plus delta Na naught by Nt naught x, and Na naught by Nt naught, that is my mole fraction of A in the beginning, is anyway equal to 1, because in the beginning we don't have any B in the balloon. So this gives me something like 1 plus twice of x. So if I now put this 1 plus 2x, whatever we have obtained in my earlier equation, we get the equation S by S naught is equal to 1 plus 2x to the power minus 2 by 3. So we will start from there now. So we have S by S naught, that is my 1 plus 2x to the power minus 2 by 3, and this gives me basically a condition how the cell thickness is changing with the conversion, right? And now first let us try to figure out, will the balloon will burst or not. The balloon will not burst in the case when the conversion becomes equal to 1. Even then the cell thickness is higher than the minimum cell thickness given, right? So the condition for balloon to burst is something like S has to be less than Sm. If this condition is not met when x becomes equal to 1, that is maximum possible conversion, in this case the balloon will not burst, right? So we can say that the balloon will not burst if this S naught into 1 plus 2 x, and I put x equal to 1 there. So into 3 to the power minus 2 by 3 happens to be more than Sm, and in that case we should have something like S naught by Sm should be higher than 3 to the power 2/3. So if I choose my initial thickness in a manner that S naught by Sm is higher than this, in that case the balloon is not going to burst. But in case the balloon burst, in that case we will use this condition, right? And we can of course find the conversion from that equation. So once the balloon burst, that can only happen if my S naught by Sm is less than 3 to the power 2/3. Once it burst, then we have Sm by S naught is equal to 1 plus 2xm, that is the conversion once the balloon is bursting, to the power minus 2/3, and this gives me Sm by S naught to the power 3 by 2, actually minus 3 by 2, is equal to 1 plus 2xm, and from that we can get the conversion once the balloon is bursting, and from there we can find the concentration once the balloon is bursting, that is Ca is equal to Ca naught into 1 minus xm, but we need to also consider the volume change. So it is better to use the equation Na is equal to Na naught into 1 minus xm, because there is a volume change in the reactor, and from there we can find the number of moles of A that is released once the balloon is getting burst. So with that, we have done some examples on the mole balance of reactors, and now until so far we have discussed only isothermal reactors where there is no temperature change. Let us now proceed to the case when there can be a temperature change in the reactor, that is the reactor can be non-isothermal, which is more reasonable situation, because the reaction typically is either endothermic or exothermic, and we need to therefore have arrangements to maintain temperature in the reactor, right? So therefore what is more likely is the reactor actually is non-isothermal as opposed to completely isothermal. Of course we can maintain isothermal conditions in certain cases, but in general the reactor can be non-isothermal, right? So let us look at that, how can we model this. In order to model this, in addition to the mole balance, we also need to account for the energy balance on the reactor. And for the energy balance on the reactor, what we will do is start from the general energy balance equation that looks very similar to the mole balance equation, in the sense that we have to again do in minus out plus generation is equal to accumulation. But what now we have to keep in mind is, now we have an input of the energy in the reactor and the addition of the energy, or the work is getting done, and then the output of the energy from the reactor, as opposed to the number of moles in the earlier example, right. So, what we can see, the energy that is coming in the reactor, it is basically the enthalpy of the feed that is entering the reactor. Let us say, for example, you have a hot fluid that enters a reactor. In that case, the hot fluid carries a thermal energy as it comes in. In a similar manner, if a hot fluid leaves the reactor, the hot fluid will carry a thermal energy along with as it is going out, right. And the way to account for that is to express the energy of the feed stream as something like the molar flow rate multiplied by the enthalpy per unit mole of the incoming stream, that is Hi naught, and the same thing for the outgoing streams, the enthalpy per unit mole. You may argue that why we are looking at enthalpy and not internal energy. What we have to keep in mind is basically my enthalpy is my internal energy plus PV. This is what comes from temperature, the E. The second part essentially corresponds to flow work. So, whenever something is coming in and filling the tank, it is essentially doing a flow work on the reactor, right. In addition to flow work, there can also be a shaft work done by the reactor system. And the shaft work, for example, can be, let us say you have a stirrer. The stirrer will require some work, right. So, in that case, the work done by the system will be negative. On the other hand, I can also attach a turbine. So, whatever energy I have in the reactor can be used to run a turbine, and we can extract the energy from the reactor in that particular way. In that case, the shaft work is going to be positive, right. So, the convention we have used is the shaft work done by the system is considered positive and done on the system is considered negative. Similarly, we will also have a heat added to the system, that is, for example, coming from a jacket in the case of a jacketed reactor, right. That is the heat that we are adding in, that also has to be accounted for, and basically the heat added and the shaft work done basically forms the generation terms. This is the energy getting added and this is the work done by the system. So, therefore, I added a plus sign here and a minus sign here, and please keep in mind that we also have an additional work, flow work, that is not coming in this equation because we have written in terms of enthalpies the in minus out of that, right. So, this entire thing becomes equal to the accumulation of energy. This E sys essentially is the energy of the system, that is my reactor, and now we have the energy balance, right. So, this is pretty much true for any kind of reactor. You will have enthalpies coming in. In the case of batch, we can set it equal to 0, just like whatever we did for the general mole balance. We can use this general energy balance for any kind of a reactor. So, we have a enthalpy coming from the incoming stream, enthalpy that is going out, there is a heat added, and then there is some work getting done. So, all of this is already accounted for in this particular equation. Now, we will try to simplify this a bit further and apply it for the reaction example that we are doing. So, what we will do is, the very first thing that we will do is, we know from stoichiometry that I can define a quantity theta I, that is the ratio of the molar flow rate of species I with the molar flow rate of the limiting reactant, which is A in this case. And again, from stoichiometry, for the outgoing stream, I can introduce the language of conversion and the stoichiometric coefficient. So, whatever we got from the stoichiometry, I am basically plugging it in the equation, and then we can do certain simplifications, and basically we will have an equation coming like this. What is important here is that if you do that, you will get a summation over the stoichiometric coefficient multiplied by the enthalpy. that basically is the definition of my heat of reaction, right? And this is going to be positive if we have endothermic reaction, and it is going to be negative if we have exothermic reaction, and other terms remains more or less same. Essentially what I have done here is simply plugged in the stoichiometry that we know already and use the definition of the heat of the reaction. So going further, we can make now few more assumptions to express the enthalpies in terms of temperature. And the assumptions that we make is, first, there is no phase change. You may know that enthalpy may change by two ways. One is a sensible heat that corresponds to the change in temperature for a given phase. That is basically what we know as Cp delta T kind of a thing. And there can also be an enthalpy associated with the phase change where there is no temperature change. Let us say when water becomes steam, there is a latent heat that is coming in. So there is complete phase change, there is no temperature change. So we will look at the cases when there is no phase change. In that case, we only have sensible heat. And in that case, we can express the enthalpy at temperature T as some sort of an standard enthalpy defined at some reference temperature. Typically for liquid it is 25 degrees Celsius plus the sensible heat change, that is basically Cp dt integrated from the reference temperature to a temperature T, right. Now Cp in principle can be a function of temperature, and in general it is a function of temperature. You may have seen relations like this: Cp is equal to A plus Bt plus Ct square, but that dependence many a times is weak. And when that is true, we can use an assumption that the heat capacity is constant, and in that case we are going to have basically something like this. We have dropped the integration, and going further, if I assume that the process is adiabatic, in that case I can drop this q dot term. And if I assume that there is no shaft work, there is no impeller or stirrer inside the reactor, that is true for a plug flow reactor anyway, or there is no turbine extracting energy from the system, in that case we can drop the shaft work as well. And then finally we can assume steady state. In that case I can drop the right hand side again, and then we have a much simpler equation where now I have additional definition. Just like heat of reaction, we can also define a delta Cp, that is basically a sum over the multiple of stoichiometric coefficient and the heat capacities of the species. So now let us apply that on a simpler example. So we have a first order liquid phase exothermic reaction. That means my delta H reaction is less than 0. It is happening in a adiabatic PFR, so we can assume that Q dot is equal to 0. And we can also assume that there is no shaft work, Ws dot equal to 0. And what is also being said is that the heat capacities of the species are not different, they are the same. If that is true, then in that case the delta Cp, that is sum over the stoichiometric coefficients multiplied with the heat capacity of species, that will happen to be 0. That will simplify our energy balance. This term will get dropped. This term will get dropped. And then we will have a much simpler energy balance. If I also assume that the temperature of all the species entering is pretty much same, right? So I had some Ti naught earlier, but if the feed is well mixed, I can assume that the temperature of all the species is same, that is T naught. And then we have an equation for the conversion in terms of temperature T at a particular point, temperature T naught at the inlet divided by the heat of reaction, right? And what is to be noted here, that this is a linear relation. The x essentially is going to be linear in T, and for temperature equal to T naught, x essentially becomes 0, and the slope here is positive because we have exothermic reaction, delta H is negative. So therefore denominator becomes positive. So we have a positive slope starting from x0, and then we have a linear equation, right? What is to be noted here is this is not the only equation for the conversion. This is what is coming from the energy balance. In addition, we also have mole balance in this problem, right? So the mole balance will also give you an equation for the conversion. In this case, it's a PFR. So basically, we can use the PFR design equation, and then by integrating, we can get an equation for the conversion that is coming from the mole balance. What is to be noted here is now this rate constant is also not constant anymore because temperature is changing. So we can write the rate constant by the Arrhenius relation, and many a times it's convenient to basically use the definition of rate constant at some temperature T naught and then apply the Arrhenius correction as I am doing here, but you can write in different ways as well, right? So we have now basically two equations for the conversion, one coming from the mole balance and one coming from the energy balance, right? What's the solution to this problem, right? As you may expect, the solution is going to be the intersection of what we get from the energy balance and what we get from the mole balance, right? And what the intersection corresponds to is essentially the conversion in the adiabatic condition, because we assumed adiabatic condition here, and the temperature in the adiabatic condition, that is what, because we assumed adiabatic condition here, right? So we have a crossover that will give you basically what conditions you will achieve in the reactor. So you can imagine the energy balance is providing an additional constraint that must be satisfied in addition to the mole balance, and therefore we need to basically solve these two balances together in order to find the conversion and temperature in the adiabatic condition, and the same thing will apply for other conditions as well, right? So with that, I want to conclude the discussion on energy balances so far. In the next lecture, I will basically extend this to an idea of to reversible reactions, and you will see what complications arise when I apply the energy balance on the reversible reaction, right? So with that, I want to conclude this lecture. Thank you so much.